Welcome back. What I'm about to explain is about sine cosine functions. They are the backbone of the AC analysis we are going to encounter both in lab as well as in chapter 9, 10 and 11. So I want to briefly go over this type of a signal. It's different obviously from a DC signal you have seen or a unity, a step function you have seen so far. It's not going to be flat, it's changing in time. I'm not good in drawing, and I want just to explain how a cosine of t or omega t is going to play. Now, if you have cosine of t, you can easily say my x-axis is t, but if you say it is cosine of omega t, you have an option of doing this in t, or you can do this in omega t. So this axis is basically in your hand. Now, there are a few critical points and critical information. For example, if omega t or t is equal to 0, what do you get? This one is going to be cosine of 0. This one is going to be 1. So obviously, at this moment, this is going to be 1. Now, imagine if omega t, and by the way, remember omega is equal to 2 pi f. And f is going to be 1 over t. I'm going to explain that in a moment. If omega t is equal to pi divided by 2 radian per second, pi divided by 2, this one 90 degrees, and cosine of 90 degrees is going to be 0. So that's going to be pi divided by 2. If I have omega t as equal to pi, I'm going to get cosine of 180 degrees. Please remember this, unity circle, and that's my x-axis, this is my y-axis, and this is 0, this is going to be 90 degrees, this is going to be 180 degrees, this is minus 90 degrees, and this is minus 180 degrees, right? So you remember the unity circle, which is going to be beneficial in terms of even j. Cosine of 180 degrees, this is plus 1, minus 1, 0. This is the representative of cosine, 0 again. So this case is going to be minus 1. And then if omega t is equal to basically 3 pi divided by 2, 3 times 90 degrees, 270 degrees, or minus 90 degrees, I say this is equivalent, not the same as equal sign. So then obviously cosine of omega t is going to be 0. So what do I get? For pi, I'm going to get minus 1. This is pi. For 3 pi divided by 2, I'm going to get 0. And obviously cosine of 2 pi is going to bring you back into the same point you began, and obviously that's going to be the maximum once again you are going to reach. So let me extend this x-axis, and the maximum is going to be this one again, plus 1, okay? You have been able to identify a number of critical points, maximum, minimum points, crossover points. These are crossover points that they pass through zeros. That's why they are important. Now, in terms of the signal itself is actually periodic. Now, what do we mean by period of a signal? By period of the signal, we say that if you pick up any point on the curve, any point, okay, this one, you need to draw a line horizontally in your mind. So let's draw a line horizontally in my mind. Now obviously, that's an indication of the height I'm looking at. This height is the same as this height, is the same as this height. I know, right? Because that's the horizontal line in parallel with the x-axis. Now, although this has the same height as this, I'm not going to use this. Not only I want the height to be the same, but I want the trajectory to be the same. This one is going up and this one is going up. The slope here and the slope here is the same. If I could identify these 2 points, then this is my t, the period of the signal. Now you go into the lab, you're supposed to do that. Now some of the frequencies are actually shown on the scope. You can actually read the frequency in hertz, but also you can read the period in second or millisecond, nanosecond, microsecond. But generally speaking, the way we do it is this. We make sure that the sine cosine function, the cosine function, first of all is symmetric. The positive maximum and the negative maximum is the same. This area is the same as this area. There is an official definition of what a symmetric response is. Let me not get into that. Then if you pick up any point, for example this one, this is maximum plus 1, this is maximum plus 1, that's one period. This is 0, not this one, but this one is the same 0 because it goes up, that's one period. This one is going down, and this one is going down, that's one period. You got yourself a t. Now, if you know what your t is, 1 over t is going to be your frequency, and that's going to be in hertz. This is in seconds, and this is going to be in hertz. Now, omega is 2 pi f. It's 2 pi divided by t, and omega is radian per second. This is inverse of a second, but that's a radian per second. So that's the difference. Okay. Now, allow me to basically look into sine function. I want to clean up a bit. Let's try have the sine function plotted on this one. Okay. Okay. I'm going to use the red this time to identify what the sine function is. This is going to be another function. Let me call it g of t, and that's going to be sine of t, or since I want to have this the same unit on the x-axis, I'm going to say omega t. Now, for omega t is equal to 0, while this one is maximum 1, this guy is 0. So that's what it is. For omega t is equal to pi divided by 2, this guy is 0, but you can see the y-axis is a representative of sine function, so this is going to be plus 1. So I get here. Okay. When I get to pi, sine of pi, I'm getting back down to 0. Sine of pi is going to get me 0. Cosine of pi is going to be here. So it's exactly the same as the function, except that if I'm good at drawing, it's going to be a shifted cosine function. Okay? So the red one is a sine function. Its relationship to the cosine function is that it is exactly the same. However, it is a shifted response. Okay, hold on, this is a minimum, this is 0, and the list goes on. Now, inside the lab, you have a task to do, a measuring task to do. Now, I know that the cosine function has this period, and intentionally I made the same period for the sine function, but you can see that there is a bit of a shift. Either you take this one as your delta t, or you can take this one, this one as your delta t. It has to be the same point, the same value, the same slope. This one, this one, this one, doesn't matter. This one, this one. Now here is the challenge. For a complete t, I'm going to have 2 pi angle, 360 degrees. One period of the signal is a complete rotation around the unity circle. Now if I have delta t, how much is my phase shift? Theta or phi? Phi is equal to delta t divided by t times 2 pi. Now, if I am careful in terms of drawing, this is my capital T, and I can see that capital T is divided in 4 parts. 1/4, 1/4, 1/4, 1/4. So this delta T, for this specific design, is going to be 1/4 of T divided by T, just for this example, please, times 2 pi. So this is going to be pi divided by 2. I put that in a bracket to emphasize that this is a special case for the sine function. Now, you can tell me how sine function is related to the cosine function. Sine function is equal to the cosine function omega t plus minus a phi. Now, if omega t, basically if I have a shift in the amount of phi, actually I need to be careful. If this is omega t, this is going to be omega times capital T, and this is going to be omega times delta t. As long as I get the ratio, I'm fine. So if this is the number of units I see on the scope, and this is the number of units I see on the scope, I can do this division, and this is ratio-less. But if I want it to be more precise, this is omega capital T, and this is omega delta t. So you need to be careful on that. So that's going to be this phase shift I can see. So in this case, cosine omega t minus 90 degrees. That's going to be my sine function. How do I know that? You see, if I have a phase shift, the red is leading the blue. The blue is lagging the red. So the red is leading. In order to capture that leading moment for the blue one, I just need to have a minus, because this one would have to be plus 90 degrees. Plus 90 degrees, that's the leading part. This has to be plus 90 degrees to give me a 0. So that's what happens. Let me see if I can verify this relationship, this equation I got. Now you remember the formula for cosine sine function. If you have alpha plus beta, what do you get? You get cosine alpha, cosine beta minus sine alpha, sine beta. Okay, let's try this one more time. If you happen to have cosine alpha minus beta, for minus beta, this is going to change to plus, because that minus beta goes into this one. This beta is now replaced with minus beta, and that minus is going to come back. Minus minus is going to give you a plus. So cosine alpha minus beta is cosine alpha, cosine beta, plus sine alpha, sine beta. Now let's put the beta as 90 degrees. What happens? 90 degrees, cosine 90 degrees, that's 0. Sine 90 degrees, that's 1. You can see this one is equal to sine of omega t. And 90 degrees phase shift is going to be bringing my cosine function to a sine function. How do I measure this? I'm going to make sure the blue is symmetric. I'm going to make sure that the red is symmetric. I'm going to go, irrespective of what the unit of the x-axis is, I'm going to count the number of units and subunits for the period. I'm going to count the units and subunits of the delta t, and obviously if the red is leading, it's going to be minus. If the red is lagging, which means red is here, then this is going to be plus. So keep that relationship in mind. Generally speaking, how is my signal going to look like? This is the system in this class. You can see different textbooks assume different notations, and there is no harm in variety of options. But I want you in this class, for the sake of consistency, assume that you have a maximum amplitude cosine omega t plus minus phi. I just want to say phi. Obviously, if phi is minus 90 degrees, you can put minus 90 degrees in it. If phi is 63 degrees, you put 63 degrees inside. What is AM? AM, in this case, is 1. But what if this is not amplitude 1? A peak-to-peak value here is 2. 1 here, 1 here. You have 2 volts, for example, if it is a voltage you are measuring. But generally speaking, this maximum amplitude is going to be maximum AM, and this one is going to be minus AM. If it is symmetric, that's what you're going to be using for the cosine function. Whatever function is, you have to convert that function to a positive cosine function. So if I have minus sine of omega t, what do I say? Again, you can utilize the minus sign and make sure your beta is actually 90 degrees. Because if you say beta is 90 degrees, this one is 0. So I'm going to say this one is equal to cosine omega t plus 90 degrees. Just put that in. You can see exactly minus sine of omega t is going to be born. You need to know all of this. In the exam, we don't have formula sheet. So I'm assuming that all of you know the basic formula in that regard. So minus, I don't want to see a minus, I want to see a plus. I don't want to see a sine, I want to see cosine. If it happens to be a phase shift, I don't mind. Once again, before I leave this topic and attack the next one, keep that in mind. Inside the bracket, this is a time varying part. This is omega t. If I want to take derivative of f of t, for example, in terms of t, I'm focusing on this. This is not changing in time. Phi is a constant. So you need to be careful about then which part is changing and which part is not changing when the time comes in to do a derivative. Okay. Now that we have learned the sine cosine function in time domain, how do we go in frequency domain? Let me actually first consider the same function we just studied. If you have f of t as equal to am cosine omega t plus phi, where do you go? Now I want to refresh your memory about e to the power of j theta, the Euler function, the Euler equation. This is a point in the space which has the amplitude of 1, the rho is 1, and the angle is going to be theta. So this one in the space is rho is equal to 1, and theta is the angle. And we know that when we represent this in the Cartesian mode, you can have the shadow of this function on the x-axis plus j, the shadow of the same function on the y-axis. There is a proof for the right and left in the appendix B when both of the functions have, all three functions have been expanded using Taylor expansion, but you don't have to worry about it. Cosine theta is the real part of e to the power of j theta. So I can say that this is equal to the real part of am e to the power of j, my theta is omega t plus phi. I can take this as my theta and actually show it in this one. If I have it done, the real part of that function, am is constant, am is real, am is positive, it can easily come out, and that's going to be, basically, this is going to be equal to am, real part, e to the power of j omega t plus phi. Okay. If I have a sine function, how can I go about this? You have two options. If you want to say my function is sine of, let me actually assign an amplitude. Let's call this Bm, an amplitude, sine of omega t plus phi. How do I go about this? Well, we made a deal together, and the deal was that you need to present this in the form of a cosine function. So this is Bm, cosine, this is my theta, so it's going to be omega t plus phi minus 90 degrees. That's going to give me a new phi, and this is going to be my time varying component. And now I can take this to the frequency domain. It's real part of Bm e to the power of j omega t plus phi minus 90 degrees. So far so good? There is also a possibility to see sine function in the imaginary part, but I don't want to confuse you, and let's not do that at this time, unless if you have an interest, you come to us in electrical engineering and we'll give you a better understanding what the sine function can be in frequency domain. Okay. let's go and study the three major components we have. This function could be a voltage source, this function could be a current source, and we did consider, although partially, how the function in time is going to be represented as a function in frequency domain. Now I want to see what happens to my resistor, what happens to my capacitor and inductor. Then I'm going to come back and I'm going to give you a clear step as how to do this in frequency domain. We are going to pay a price for this. Remember, when I'm going to take this to the frequency domain, I'm going to ignore the transient response. All I can give you guaranteed is the steady state response. And if you have an interest in the transient response, you need to establish your differential equation no matter what the degree is. If it happens to be 10th degree differential equation, so be it. Transient response is not captured by the movement I'm trying to achieve today. There are some Laplace transform and everything else that would capture it, but I don't want to go that far. Nobody in this class has shown interest in Laplace transform. Now here's my resistor. Okay. This has a value of R. The current that goes through this is going to be I of t. I choose small letters, and as soon as the current goes in, according to the Ohm law, it's going to be plus minus V of t. I want to know how I can capture this in frequency domain. Can I actually still represent this as a resistor in frequency domain? Whatever happens in frequency domain, I want to have a current. Obviously, this current is now frequency dependent, and I want to have the same voltage. I'm going to use capital to represent this. Imagine I of t is actually a cosine function. Remember what my assumption was? My assumption is if it is not cosine, make sure it is. So I'm going to say I of t is actually A of m cosine omega t plus phi. This is a time domain signal. It goes through the resistor. Ohm law dictates that V of t is equal to R times I of t. So therefore, this is going to be R times AM cosine omega t plus phi. So I'm going to separate this. This is going to be AM R. That's my new amplitude. Cosine, that's the function I wanted to see. And I can see no more phase shift. A number of important lessons I just learned from this. First, if my I has omega as the frequency, radian per second, it's going to show both in the current and the voltage the same frequency. If this is 2 pi 10 hertz, it's going to be 2 pi 10 hertz. Inside the lab though, you're going to see the same thing. You're going to see that you apply a 300 hertz to the design, and you're getting back a 300 hertz in another part of the system. You are not changing the frequency. The second thing about resistor is this. If you have a phase shift of phi, the phase shift doesn't happen. There is nothing else. It's phi. So it's phi and phi. It's not going to be phi plus 90. It's not going to be phi minus 27 degrees. The phase shift remains the same. Whatever you gave in, you got it. The last lesson I want you to learn is this. What is Vt divided by IT? Of course, if you divide it in time domain, assuming this is non-zero, you can see AM is gone, and R is left. This is the Ohm law I just used. So far, so good. That's in time domain. Because the task is to take everything from time domain into frequency domain, I need to see how this one is going to look like in frequency domain. I know that when I apply the design, the system with a cosine sine function, I'm only interested in the real part. Because I'm interested in the real part of all the voltages and all the currents of all the components, I'm going to say, let's have peace with this process. Let's say, remove the real part and just look at the complex number, do the analysis, we are going to keep in mind that at the end of the day, I'm going to pick up a real part. I'm going to go from cosine with a special transformation into frequency domain, but if I know what that special transformation is, I want to have the inverse of that transformation. So if I say, pick up this, kick it on one side, punch it at the value, raise up the value, and so I need to reverse the same process to get back to my origin. As long as it is reversible, my process is going to be okay. So I'm going to say the way you are going to look into it, because I know everything is going to be in real. I'm going to say, take a look at this and translate this into am e to the power of j omega t plus phi. What did I do? I simply say this is the real part of this, but let's ignore the real part, the real part. Everything is in complex. Do whatever you want to do in the complex. Whatever you went through, you need to inverse it back in. So it has to be inversible. So you need to inverse it. Okay. My current in the frequency domain is going to be I as equal to am e to the power of j omega t plus phi. Now, according to the Ohm law, V of omega, it's omega dependent. There is no nothing else in that sense. So it's going to be, according to the Ohm law, I'm going to have R times I. It's going to be R times Im e to the power of j omega t plus phi. Now, you can verify that V divided by I, if you have this one divided by this one, actually this one is not Im, it's actually Am, okay? If you divide this one, if you divide this by this, it's very obvious you are going to get your R back. The understanding, the frequency is not changing, the phase shift is not changing, cosine is going to remain cosine. All I'm witnessing at this time is the application of the Ohm law, both in frequency domain and the time domain. Frequency domain and time domain. So I'm going to make a simple judgment. If you have a resistor in time domain, you can simply have a resistor in frequency domain. The value is the same. I'm just trying to establish piece by piece how the transformation is done. Time domain, frequency domain. Let's do something for the capacitor and see what the capacitor does. Okay. Here is my capacitor. The capacitor, according to the simple convention we have, this is I of t, this is going to be V of t, and the value of the capacitor is going to be C. I want to know what this is in frequency domain. I, the same direction I'm going to apply, V, the same polarity I'm going to observe. I want to see how it's going to be. If my V of t is equal to Am cosine omega t plus phi. Okay? According to the component law in time domain, how is my I of t? I of t, according to the component law, is C dvc to dt. That's my Vc. It means take the derivative of this in time domain. Now, Am is constant and also positive, no harm. Cosine omega t plus phi. Omega t is the only one that is changing in time. I'm going to bring in the omega behind. And then because this is a cosine function, it's going to be minus sine of omega t plus phi. So far so good? But I'm supposed to, first of all, this is my constant, so it's going to be AM C omega, that's so far. I'm not supposed to have a minus sign. I'm not supposed to have a sine, for that matter. I'm supposed to have a cosine. Cosine of omega t plus phi plus 90 degrees. You can verify this using the expansion rule I explained the last time. So far so good? So I have I of t, I have v of t as a cosine function, that's my assumption, and I'm going to find I of t using the component law. I want you to take this to the frequency domain and tell me what is happening. Let me use the blue. This one, according to the conversion I agreed upon, is going to be AM e to the power of j omega t plus phi. This one, according to the same convention I agreed upon, is going to be AM C omega e to the power of j omega t plus phi plus 90 degrees. Remember, I simply ignored the real part, the REAL part, because I know that's my convention to go, and anytime I want to come back, I just simply take the real part. That's why. I know my move forward and backward, what is it going to be? This one in frequency domain is this is. This one is frequency domain is this one. I want to see if between V and I in frequency domain there is a special relationship, and how I can capture that relationship in frequency domain. I want you to tell me what is happening with V divided by I. Why? Because I said if V divided by I for a resistor is a constant and it defines for me the impedance of the component, can I capture similar understanding for a capacitor? This is not doable in time domain. You can't do this in time domain. It doesn't really help you as much. So let's take a look at this and see what happens. You've got yourself AM e to the power of j omega t plus phi. Underneath, you've got yourself AM c omega e to the power of j omega t plus phi plus 90 degrees. Once again, what did we do? V of t is a cosine. Using the component law in time domain, I've got myself I of t. I'm taking V of t to frequency domain, I of t to frequency domain. I'm simply studying the relationship between I and V. Now, if AM is not 0, you can actually get rid of this. E to the power of j omega t plus phi, e to the power of j omega t plus phi plus 90, you can see that this minus this happens. So this is going to be equal to 1 over c omega times e to the power of j, this minus this, minus 90 degrees. Right? Now I know what e to the power of j minus 90 degrees is. Remember my unity circle. My unity circle, this is 1, this is plus j for 90, this is minus 1 for 180 or minus 180, and if you go look at this one, you've got yourself minus j. So if you have minus 90 degrees, you've got yourself minus j. This one is going to be 1 over c omega times minus j. In many textbooks, they put the minus j in the denominator. We know when we define what j is, that minus j is actually equal to 1 over j. This one is equal to 1 over c omega j. You see, a few lessons again we want to learn from this addition. First of all, if your incoming signal has a frequency of omega, when you go through the component, the frequency does not change. That's a very important lesson. The frequency doesn't change. Although you are going to have a phi as the initial phase shift, you are going to remedy that by 90 degrees. But in order for us to capture that 90 degrees phase shift, I'm going to capture that and dump it onto the component itself. So instead of just saying this is C, I'm going to say this is 1 over C omega J. And then I'm going to make a simple assumption. This is a complex resistor in my mind, because resistor reminds me of the Ohm law, right? So I'm going to say, if you can apply the Ohm law, V divided by I is 1 over C omega J. It's similar to a resistor to me. A resistor, pure resistor, when it goes into the complex domain, it's going to remain pure resistor. But a capacitor that goes into the frequency domain, you can capture all about it in frequency domain as 1 over C omega J. Let me give you an example. Did I capture it right? If omega is equal to 0, what do you get? If omega is equal to 0, this guy is 0. You have Am cosine phi, and that's constant. It's not changing by time. And obviously, if you take a derivative of a constant in time domain, it's going to be 0. If omega is 0, you have a DC signal, and the capacitor is going to act like an open line. So if omega is 0, open line, 1 over C omega J, 1 over 0, that's infinity. That's an open line. So if I want this to be capturing that, this is going to be an infinity for me. That's going to be an open line in frequency domain. If the frequency goes to infinity, it seems that people go back and forth, back and forth, back and forth very fast. It seems as if the capacitor really has no real impact on the movement of the people. People go in, come back fast. People go in, and you imagine you can do this extremely fast. It is as if it really doesn't matter if the capacitor is actually a short line, because the people go in before not anything happens, they go back. It's really a short line to me. That's what happens. If omega goes into infinity, 1 over infinity, you've got yourself 0 ohm. 0 ohm is a short line. How do I capture this in frequency domain? This topic may be a bit heavy initially, but the good thing is that as soon as we understand what is happening, we can take it to the frequency domain and solve a problem a lot easier than solving differential equation. So I'm going to capture everything about it in frequency domain. Let me finish the last thing, and the last thing is about the inductor. Okay. You have an inductor in front of you, that's L, and you want to know how that inductor is going to look like in frequency domain. Same direction, same polarity, small letters in time domain, capital letters in frequency domain. Imagine your I of t is in the form of a cosine function in time domain. If it is not, obviously you do your best to make sure it is in the form of a cosine function. So far so good? Let's apply the component law in time domain. V of t is equal to L di to the t, which means L times the derivative of this function in time domain. Am is positive constant, no harm. Omega is coming out, no harm. Because it's a cosine, it's minus sine of omega t plus phi. Well, you've got yourself a minus sign, that's not permitted. You've got yourself a sine function, that's not permitted. You're supposed to take this into the frequency domain and give me cosine function. So I'm going to say it's Am L omega. This minus sign goes in, so it's going to be cosine omega t plus phi plus 90 degrees. Okay, that's in time domain. What is in frequency domain? According to the agreement we had, the deal we had together, take this into the frequency domain. That's going to be AM e to the power of j omega t plus phi. Again, the real part is part of the transformation. I ignore it, but I'm going to bring it back in at the last part. If you take this into the frequency domain, what do you get? You get AM L omega e to the power of j omega t plus phi plus 90 degrees. I want to know if an easy understanding, such as an Ohm law, is applicable in the frequency domain for me. So I'm going to say, what is your V to I? I want to know if this V divided by I can be captured. It can't be captured in time domain, but it could be captured in frequency domain. So I'll take a look. It's going to be AM L omega e to the power of j omega t plus phi plus 90 degrees divided by AM e to the power of j omega t plus phi. Once again, AM, if it is non-zero, you can ignore it. This is gone. E to the power of j theta 1, e to the power of j theta 2 is going to be e to the power of j theta 1 minus theta 2. It's a subtraction. So you are going to get L omega. Omega t is gone. Phi is gone. 90 degrees is left. E to the power of j 90 degrees. What is e to the power of j 90 degrees? 90 degrees, that's j. Okay? So it's going to be L omega j. This relationship tells me that VI relationship in frequency domain for an inductor is L omega j. This is L omega j. Do you remember when we said if the inductor is facing a DC incoming signal, it's going to act like a short line? If omega is 0, this is going to be L omega, L0j, that's going to be 0 ohm in frequency domain. It means it's a short line in time domain. It does capture that. Now that we have understood what R is in frequency domain, what C and L are in frequency domain, I want to give you a systematic approach of doing this in chapter 9. Okay. Hopefully I have a space. Take this into frequency domain. Actually, let me make it bigger. I think I might need space. Okay. I tell you what to do in frequency domain. Then I'm going to go back into the time domain. So this is, let me write it down. This is time domain. This is frequency domain. This is analysis in frequency domain. This is response in time domain. In time domain. If you remember, each time I emphasize on a number of findings we had. If you have omega on V for a resistor, I is going to be omega. If you take a look at the capacitor and inductor, if either of the variables has the frequency of omega, The other variable has the frequency of omega. If you take a look at the system in front of you, you can see everyone is talking omega. If I know that's the case, all I have to do is this. Capture omega. Write it down, record this. I know when I come back, during that transition, I'm talking about j omega t, that one is going to be there, because I'm going to inverse the process. So, but I don't want to confuse you, so I'm going to have the omega recorded separately, and then when everything is done, said and done, I'm going to bring in the omega into the process. What do you have? If you have a resistor, you are going to have a resistor. If you have a capacitor in time domain, you are going to have a capacitor in time domain. Its value, though, is going to be 1 over c omega j. If you have an inductor in time domain, you are going to have an inductor in frequency domain. Its value is L omega j. If you have a voltage source or a current source, say this is going to be AM cosine, I'm just saying it, omega t plus phi. If you have it like this, you can replace it by a voltage source or a current source in frequency domain in the following way. AM angle phi. Or you can say it's AM e to the power of j phi. What happened to my omega? I said omega is the same. When I come back, I remember to bring that omega back in. But you can see in this one, it's a lot simpler, a lot cleaner. I'm going to show you a few examples to see how this is done. Then, I'm asking you to imagine that your system now is resistive. Resistors are resistors. Capacitors are complex resistors. Inductors are complex resistors. But everything is resistor now. If everything is resistor, you can apply the same thing you learn pre-midterm. Do nodal, do mesh, supernode, superposition. Everything that you can do, please do. Source transformation. So you can do nodal, mesh, or supernode and supermesh. You can do superposition, and you can do source transformation. Everything as if you are facing resistors in your system. Transform, source transform. Assuming everything is resistor now, except some values are actually complex, then you're fine. Then bring it back in. Find the variable of interest. Find the V, find the I, whatever the variable of interest is. And suppose that your variable of interest, I'm just going to call it V at this time, V of, suppose your V is in the following form. V of X, unknown, is equal to some amplitude, angle, theta. Eventually, it's going to be a complex number. And if that complex number is in polar domain, remember at this stage, Cartesian doesn't work. You might want to do this in Cartesian, that's fine. But for the last step, you need to have it in polar domain. Imagine your number is 5 angle 32 degrees. Suppose you have it. Then you are going to say this is going to be k e to the power of j omega t plus theta, and then it's going to be k cosine omega t plus theta. You see what happened? I still have omega. I know everything is in omega. I still have omega. I've got my theta through variations of the analysis. I've got my k, it's going to change. I have a polar representation. I bring in co-omega first, and I also, if you remember, I took the real part of that complex number. I took the real part. So you remember I took a V. I forgot the real part initially because I wanted everything to be in the simple form. Remember what we are trying to do. Solving this in time domain is extensive, expensive, time consuming. If you are not interested in the transit analysis and you don't want to do Laplace transform or anything of that nature, take this into the frequency domain using a simple transformation technique. Solve your system as if everything is in resistive mode. Take the polar representation and bring it back to the time domain. You're done. This is called a steady state response of that scenario. Now what I'm going to do in the remaining part, I'm going to go in and solve a couple of questions so that everybody feels very comfortable what we are trying to achieve. Okay? Let me grab a simple case. Page 387, example 99. Actually, yes, that's all right. I'm going to do example 99 and then we can do practice runs in a moment. So here is my case. That's 5 ohm. I have a capacitor in time domain. Its value is 0.1 farad. That's really big, but that's fine. This is my variable of interest in time domain. And then I have an incoming signal. And it's going to be 10 cosine 4t. That's called my Vs. Because when you go into the exam, we are going to ask you questions from chapter 7 as well as chapter 9 and 10. You need to be able to step back and see which chapter you belong to. Sometimes, as you solve chapter 7, your mind is racing to do analysis in DC time, DC input. You go into the next questions and you are still in the DC mode running because your engine is still running, right? So what happens is that you think that this is a DC system and you apply. Why? You have one capacitor. Good. That's what clicks. One storage element. But you don't have the switch. You have an incoming signal that is an AC signal. As soon as you see an AC signal coming in, it means you have to apply the technique we talked about just now. Although you have one capacitor, but that's it. After I make that understanding that this is an AC circuit I'm trying to analyze, then the question is, do we have the right setting? Is this a cosine function? Is this a positive amplitude? Yes, it is plus 10. Yes, it is cosine. The setting is right. What I'm going to do, I'm going to capture omega. Omega is 4t. You see, 4. This is omega t, and therefore omega is 4. So I am going to capture that. I'm going to utilize that when I want to do transformation, but that's all it gets. Let's take this to the frequency domain. What happens to my source? There is no phase shift. The phi is 0. Because the phi is 0, this is going to be 10 angle 0. This is 10 angle 0. You can say this is 10 e to the power of j0. You can say this is actually 10 in frequency domain. Because my phi is 0. It's given this way. A resistor is going to be a resistor. A capacitor, you can actually draw the capacitor if it makes you more comfortable like a box. And then how much is this capacitor? This is going to be over C omega j, and this is going to be 1 over. C is 0.1, omega you capture it separately 4, and this is j. So it's going to be 1 divided by 0.4. This is 2.5 over j, or it could be minus 2.5 j. Remember, 1 over j is minus j. In this class, the impedance of a capacitor is always negative. If you got a negative impedance, you could easily say it is coming from a capacitor. Not necessarily so all the time though, because it might be a combination of a capacitor and inductor. But generally speaking, a negative impedance means it's a capacitor. your capacitor should exhibit a negative value in this class. I have a resistor, I have an incoming source, and I want this, and I'm going to write this down in capital V. How much is that? You remember the voltage division principle we applied? You can do it. V is equal to 1 over C omega J, the R rule, divided by R plus 1 over C omega J times incoming voltage. I'm going to accept this as capital S. Okay. So what do I have? Actually, I just wrote it parametrically, but you don't have to. This is minus 2.5 minus 2.5J divided by 5 minus 2.5J times incoming signal, which is 10. Now we know what to do. We know how to do this by the calculator. This part, I'm not going to do that, but you definitely need a lot of exercise to be able to utilize your calculator fast. This is going to give you V in frequency domain. V in frequency domain is, according to the book, is 4.47 angle. I'm assuming it's correct, 4.47 angle minus 63.43 degrees. This is now in polar domain. It's in polar domain. I needed that to be in polar domain. I want to take this V as this into the time domain response. V of t is equal to, amplitude is 4.47. It's definitely cosine because I'm assuming everything is in cosine. My omega is 4, I'm going to have omega t. And then of course I'm going to have angle. So it's minus 63.43 degrees. That's my time domain response. This is the steady state response that happens to be across this. This is cosine. It's going to be cosine, but it's going to be a phase shifted cosine by the amount of 63 degrees. Let me go in and grab a different example. Let's grab a bit of a complex example this time, and I want to do mesh and nodal, and hopefully we capture all the information. So let's go back. This is page 395. It happens that the information given to us is actually already in frequency domain. 0 degrees. Someone has did that transformation for us, 12 ohm. Minus 4J. No, this is plus 4J because the inductor is supposed to be positive. This is minus 3J, that makes sense. Capacitor is supposed to be negative. This is 8. This is going to be inductor again, 6J, and then 8 ohm. And then I have 2 ohm and minus 4J. I need to raise it up a bit. 2 ohm and minus 4J. Okay, someone has done the transformation for me. Do I know what omega is? At this time, no, unless the question tells me, and the question did not tell me what my omega is. So all we are asking of you in this time is give me the answer in frequency domain, because I can't take it back to the time domain. In order for me to take it back to the time domain, I need to know what omega is. Of course, you can leave it as a parameter called omega. Is this a right setting? Yes, inductor is supposed to be positive. Capacitors are supposed to be negative. Positive, okay, everything is fine. This is angle 0, which means e to the power of j0. That's actually 1, so this is actually 50. So this is 50. So my omega is just an omega. We are supposed to be able now, at this time, after so much exercise, to apply the nodal or mesh on this scenario. You have only one source, so superposition really doesn't matter. So let's take a look. How many nodes do I have? The same thing applies. This is 0, this is 1, this is 2, this is 3. If this is my reference node or my ground node, obviously I have a voltage source, and the voltage here is going to be plus minus the minus sign. You remember those stuff? The minus sign is 0, the plus sign is going to be 50 angle 0. That's in frequency domain. Let's call this Vx, let's call this Vy, let's call this Vz. Right. The nodal equation that you need to solve the system for. So this is Vx minus 50 divided by 12. Vx is the biggest voltage now, plus Vx minus Vy divided by 4j. Vx is the biggest one over Vy, and then Vx minus Vz divided by, you can actually see this 2 ohm and minus 4j in series. Now that they are resistors, now that they are in series, you can actually sum them up. So this one is going to be 2 minus 4j. But you have to make that connection first. You have to make sure they are in series before you go ahead and do this. This is supposed to be 0. Let's take a look at node Vy. At Vy, we are assuming that Vy is the biggest voltage for the sake of writing the equation. Vy minus Vx divided by 4j. Vy minus 0 divided by minus 3j. Vy minus Vz divided by 8 as equal to 0. Okay, this one, Vz minus Vy divided by 8. Vz minus Vx divided by the combination of two resistors now. Remember, this is the beauty of frequency analysis. It's really easy at this moment. Vz minus 0 divided by 8 plus 6j as equal to 0. Okay? Now, the next step you have to do is this. Grab Vx only. So Vx is going to be 1 over 12 plus 1 over 4j plus 1 over 2 minus 4j. That's my Vx. I'm going to do the first one, but the rest I'm going to leave it with you. Plus Vy. When I say Vy, all I have is 1 minus 1 over 4j. Plus Vz, all I have is 1 over 2 minus 4j as equal to my constant, 50 divided by 12. Do you really need to simplify this? No. You don't have to simplify this. But of course, simplification shouldn't be taking you too long now that you can actually use the calculator. Use the calculator and simplify this if you must. But you don't have to. And that's going to be preventing you from making some mistake. So the next time I'm going to have Vx, Vy, Vz, constant. The next time, same order, Vx, Vy, Vz, that's it. Okay? Now, this happens to be 3 by 3 system. We didn't mean to make it this difficult, it happened to be, but you know how to calculate the determinant of a 3 by 3 system. I'm going to refresh your memory in a moment. This is nodal equation. If you want to do mesh equation, what do? You have one loop here, you have another loop here, and assign the loops clockwise, and you've got yourself 3 primitive loops. 1, 2, 3. When you write it down, the current in this loop is going to be the biggest one, the master. Everything else is the slave. When you write it this one, this is the master, everything is a slave. When you write it this one, this is the master, everything else is a slave. You write it exactly the same way you did pre-midterm. The only difference now is that in elements are actually in complex domain. That's all. Okay? Let me refresh your memory as to how to do this. I'm not guaranteeing that the final exam or the bonus test does not have a 3x3 system. It could, so I'm asking everyone to be ready for it. 4x4 is obviously not a question for us, so I'm not going to bother that. If you happen to have complex number, A1, B1, C1, A2, B2, C2, A3, B3, C3. How do you calculate the determinant of this system? How do you calculate the determinant? That's the question. Whether it's delta, system determinant, delta X, the determinant dedicated for the column X, delta Y, delta Z, you have a 3x3 matrix. You have a 3x3 determinant to solve. Now, if you remember, this is the way we did it. We copied the first and the second column, and we actually put it in. So it's going to be A2, A3, B1, B2, B3. You see, this is not really difficult anymore. You need to go diagonal. Sum them up. Minus, open bracket. You need to go anti-diagonal. Sum them up. Close bracket. You're done. So the way it is going to be, let's do that. A1, B2, C3. That's the first diagonal. Plus B1, C2, A3. Plus C1, A2, B3. That's the 3 diagonal. This one, and this one. I put them intentionally inside the bracket. Minus. Open another bracket and sum up everything anti-diagonal. Remember, I intentionally opened up a bracket. Anti-diagonal, B1, A2, C3, B1, A2, C3, A1, C2, B3, C1, B2, A3. Do you have to simplify this manually? As long as you can have a visual contact with the determinant, you simply punch this into your calculator. You put A inside the bracket if it is complex, B inside the bracket, C inside the bracket. You have multiple brackets, that's the only challenge, but everything else is going to be fine. Now, the only difference between the pre-midterm and the post-midterm in terms of calculator is this. The calculator could take a 2x2 or a 3x3 system pre-midterm if everything is real. I've had seen a couple of my students who did complex matrix on one shot on the calculator, but I don't know how they did it. I may ask them to come back and give us a clue, but let's assume that at this time the calculator cannot do a 2x2 or a 3x3 system of equation. So you need to manually first visually connect with the matrix, write it down on this side, pick up the calculator and do the calculation. As the last thing I want to say is this. This is going to cover my chapter 9 and chapter 10. Basically, the questions assigned in chapter 9 are a gateway for you to have some exercise. The solutions are posted. I did not assign anything from chapter 10. So practically, every question of chapter 10 is open for bonus test and the final exam. And you just need to solve a couple of topologies, both in terms of nodal, mesh, and superposition. That's the way we do it. A couple of issues that I want to raise at the last time. So basically we finished all the theory at this time. First, those of the students who only attempted to solve 1 or 2 exam shells, exam questions from last year's or the ones posted, they did not achieve the desired response and conclusion after the midterm. It is not sufficient just to solve one set of exam questions. You need to solve as many as you can. Those of you who solve as many as you can, you come in, you can see that the exam is going to be extremely easy. There is nothing called difficult or easy in this class. It all boils down on the exercise. So that's the first thing. The first thing is just do not rely on one set of solutions, one set of exam questions. It's not enough. You have to do quite a few, and I encourage you to do that. The second thing is the strange phenomena we have seen in this class versus the similar classes we have had in the past. The success I have enjoyed, and I'm honored to have enjoyed in this term, is beyond my imagination and beyond my belief. We have had more difficult makeup tests thrown at everyone, and everyone did an excellent job. We have had quiz number 4, for example, on Friday that was supposed to and meant to be more difficult than on Wednesday's class, and still everybody did with a flying color. We haven't marked it yet, but everybody was happy. The clips are working. The YouTube is working and is helping you. Please listen to the YouTube and learn and come and let us know what your mistakes are, what your problems are, and we will be solving this. We have had a shining class. You may face a difficult exam in the final, but it doesn't mean you cannot overcome this. You have done it. You are very close to a desirable outcome, and I really encourage you and stress that please do exercise and get to the response, brainstorm with your friends, then take a look at my solutions. First, individual works. Don't do group work. First, individual. Then do group work. Then take a look at the solutions I posted on the blackboard. Then you should be fine. There is nothing, there is no mystery. We will be asking you about everything you have learned from the beginning to the end. Of course, when I say nodal mesh superposition and source transformation, I'm asking you pre-midterm, but of course with the concept of the complex domain. We are going to ask you 9 questions, 3 hours, 20 minutes each. Please do your best, make us proud, enjoy the session as much as I did and Dr. Muhammadi did, and all the TAs are actually here to help. I appreciate your response, and let's celebrate when the final exam is over. Thank you very much and wish you all the best. Thank you.